Hi friends, welcome to this channel. Here we are going to look at this problem. Convert binary search tree to sorted doubly linked list. So in this video, we are going to explain a solution based on recursion. Before we do that, first there are several things we want you to notice. First is the binary search property. Basically, it says that there recursively holds that the left subtree maximum value is less than the root value is less than the minimum value of the right subtree, right? So this is the one point. Another point is that if you do in-order traversal of a binary search tree, you are going to get a sorted list, right? So this is the second point. The third point I want you to notice is that this requirement. For a circularly doubly linked list, the predecessor of the first element is the last one, and the successor of the last element is the first element, right? So here we want to do it in place. This is also an important assumption. So we need to return the pointer to the smallest element of the linked list. So with that said, for example, this example 1, the smallest element should be 1, right? So similarly, like this one. The constraints are the following. The number of nodes in the tree is in this range. This is given by a closed interval. The values are in between -1000 and +1000, and all the values of the tree are unique, right? So here you see this bound, and you see this bound. Yeah, it's can make all the values unique. This also consists. So with that said, I guess we are ready to do the coding. So our plan will be the following. So we first treat an edge case. So the plan of coding will be the following. First, treat an edge case, and then write a hyperfunction. So writing the function has a lot of freedom because you can use whatever function signature to adapt to the need of the problem, and then do the return. So this is the big picture. Now let's look at the coding. First, I'm going to, if not root, so we're going to return none, or just the return. So actually, if you use recursion, sometimes you also need to use this null case as a stop condition or bounding condition. Some textbook also say it's a base case, right? So now let me write a function that is we changed the tree to doubly linked list. So here the return type I'm going to return is the head and the tail of the result. So essentially this is the in-order traversal. So now I'm just going to call this f, or you can call it hyperfunction helper, right? So first, if not node. So in this case, I'm going to return null, right? So here we cannot write just a nothing, right? Because here null means that we return a tuple of list 2. So this is the one. And then what we are going to do is to do the same thing for the left subtree and the right subtree. So we have left head and left tail. That's going to be f, so node left. Because we have already considered the base case, so this is also always legitimate, because this can be a null, right? If null, so this 2 will be null. So we do the same thing for the right. So right head and right tail is f node right. But here there's one thing to notice, that is for the left subtree, the left head has the the smallest value. The left tail has the largest value. Well, for this part, the head actually has the smallest value, and this is the largest value. So now let's make some arrangement. So first, if there is a right subtree, left subtree, then what we are going to do is to connect the left tail. So this is the largest value, of course, right? So to node, right? Because the largest value in the left, then the successor will be the node, right? So then what we want to do, so if this one, so we have the left tail, so then the node left would be a left tail, and the left tail, the right will be the node, right? So this is the one. Another one is that if there is a right subtree, in this case, so we need to connect node and the right height, because the right height will be the smallest value that is larger than node. So in other words, our height is the next of node, right? So basically, if our height, so what we want to do is our height left, right, is the node, and node right is our height. You can think of this for all the internal nodes. So the right pointer points to a larger value, right, and the left point to a smaller value. So this is a work where we have done. So now we want to do for the first one and the last one, right? We want the first one, it's due to the requirement here, right? The first element, the previous one of the first element will be the last element, and the successor or last element is the first element. So what we want to do is this. The height will be the left height or node, right? Notice this expression. If this left height is not null, so we're going to set the height to be the left height. Otherwise, it will be the node. So same thing for tail. The tail will be either the R tail or node, right? If you do not have an R tail or it's null, then the node, the root, right? Then what we want to do, we want to set, so we just need to return the height and tail. So here I didn't make some connections like here. We can do it after we call this function. So this will be our hyperfunction. It does the major job. So now what we want to do, so we call this function height, tail, and then it's going to be f and called on the root. And then we connect the height and the tail, right? This is by the requirement. So because we have already treated this case, right? So here the height and the tail will be not null. So in this regard, so we can do height. So this corresponds to the smallest value, right? So the left, so it should be in general pointing to a smaller value, but this is the first one, so it's going to point to the largest value, that is the tail. So similarly for tail, for the right, it should in principle for the internal node will point to a larger value, but because this is the largest one, so it's going to point to the height, and then we just need to return height. So this will be a full code for this problem. So now let's quickly test it. Yeah, it passes the two test cases. Now let's look at the generic case. Yeah, it passes all the generic cases. So with the coding finished, let me make one or two comments. The first comment is that for tree, binary search tree, or in general graph, so lot of the time, if not most, so you can think of a solution based on recursion. But sometimes if you want to understand the finer details, you can consider doing it via iterative format. This is the first comment. The second comment is on our channel. So we have a channel which contains a lot of problem in the binary tree list. You are welcome to check out that playlist. Meanwhile, you can for sure check out other playlists to practice. With that said, that's it for the current video. Thank you for watching.